Okay, AP Chemistry kids, this is a video on buffer solutions, what they are and how they work and how to calculate a simple buffer solution. The first thing we want to talk about is that a buffered solution is a solution that has a weak species, so either an acid or a weak acid or a weak base, and then it would have its conjugate salt in there. So there would be a common ion. And you can see in this slide here that the common, so when we take a look at the common ion, it is the acetate ion here. You've got acetic acid and you've got sodium acetate. So that's the common ion for this buffer solution here. And when you add either an acid or a base, the pH is very, very minor as far as how much it changes. That's because of this ratio of a weak acid to its conjugate in this example. So I want to talk a little bit about buffers, and they're really everywhere in our world. They are in, some citric juices that you would drink, like Country Time lemonade comes to mind right now, that it has a pretty big buffer system. So you're tasting that tangy thing, that tangy taste, but you're not, it's not really irritating to your throat when you're drinking lemonades. Some types of lemonades, they're buffered. Sometimes you hear aspirins, like Bufferin is a type of acid that is buffered as well. And the big one that you should kind of be aware about is that your blood is really, there is a buffer system that's in your blood. It's actually our carbonic acid bicarbonate buffer. And your blood can only function at a really short pH range, very narrow pH range, as you can see here, like from 7.35 to 7.45. Yet when you exercise and you're taking in a lot of CO2, you're also producing lactic acid, and it's actually the lactic acid that functions, and that breakdown can change the pH in your body. You have a CO2 slash bicarbonate system, carbonic acid bicarbonate buffer system that compensates for that. At the end of this page, I have a link if you want to know more about that physiology of how your blood changes, or how your blood is buffered, I should say, by exercise, or how exercise, I should say, really affects your blood pH and how your body responds to that. So you can take a look at that link below, okay? So how does a buffer work? Well, a buffer works. Remember what a buffer has is a buffer has a really high, relatively high concentration of a weak acid and its conjugate. Okay, we're going to look at this weak acid buffer system. You could also have a weak base buffer system, but for this example and how they work, I want to talk about a weak acid buffer system. And so you have in relatively high concentrations the acid and its conjugate base, okay? And so there is a ratio of acid and conjugate base that we really say is virtually constant. And as you can see right here, if we have a buffer with equal concentrations of weak acid and weak bases, it looks like here, okay? So we have equal concentrations of my acid HX and its conjugate base, the X minus anion, okay? So now, looking up here, if we had, and I know I have X below, and here I have the acid represented as HA, but you should recognize that those mean the same thing. If I have an acid, a weak acid, and I expose it to some base, some hydroxide, what's going to happen is this hydroxide is going to react with the H in that weak acid to make water. And what you're left with is A minus, okay? So the concentration of this A minus will increase just a little bit, but not significantly, where that ratio can stay still pretty high. So in a sense, the weak acid from the buffer absorbs, if you will, the hydroxide from the base, so it doesn't change the pH that much. Now, what if you were adding acid. So here I'm going to have acid. Well, what component of the buffer will we want to react with this H plus to absorb it? Are you thinking the same thing I am? Indeed, it would be the conjugate base. So what happens is the conjugate base is going to react to make HA, okay? Now, what this does then is that this conjugate base is absorbing the acid component that it's been exposed to, and it's going to keep it bound up as that weak acid, as you can see right here with the buffer addition of an H+. And so yes, still those, as you notice, those concentrations, they do change, but they're still relatively high. And so that's how a buffer works. It will basically absorb hydroxide, and when it's absorbing hydroxide, that OH is reacting with the acid to make water, as you can see here in this equation, or it will absorb the H+, where that H+ is reacting with the conjugate base to make more acid. That's how a buffer works. Okay, so now moving on, if we're looking at key points of a buffer system, the big thing you should know, they're weak species. So they are either weak acids or weak bases, and then they contain that common conjugate species as well. So sometimes you'll see, like in a AP test question, they'll say if you have something like this and NaCl, and they'll ask you, hydrochloric acid, NaCl, would that be a buffer system? And the answer is no. This is not a buffer because this isn't weak. HCl is a strong acid. So it has to be a weak acid or a weak base and that common ion. When you are asked to calculate the pH after, so this would be the pH after the addition of an acid or a base, okay, then you would have to deal with some stoichiometry first. Oops, that didn't work out so well. I didn't mean to totally underline that. So you would have to deal with some stoichiometry first. So you'd want to do that first, and then you do the Rice tables. And in your textbook, let me just make sure, because I'm not covering that, you will want to look at example 15.3, okay? So that's a 15.3. You're going to want to look at that example because it's having you calculate the pH after you've added acid or base. So that would be a good thing to take a look at. You can see how they're doing the stoichiometry first, followed by the Rice table. What I want to do here and finish up in the next few minutes that I have here, I want to do just a very quick example of a very, very easy buffer problem, okay? So in this problem here, you'll notice that we have acetic acid. So you should say to yourself, I know that's a weak acid. And then look at, we have sodium acetate. And notice that they have that common ion. They're giving you the Ka, and they're asking you to find the pH of that mixture, okay? So when I'm calculating the pH of that mixture, the thing that I want to be thinking of are what are the major species, okay? So what is a major species here? I would consider would be the acetic acid. So there's the acetic acid. The sodium acetate, because it's group 1, sodium is going to completely dissociate. It's very soluble. There's going to be a lot of sodium ions. There's going to be a lot of acetate ions. And of course, there's also water that is in the solution. So these 4 components, the acetic acid, the water, the sodium ions, the acetate ions, those are the things that are in water that are the major species. Now I ask myself, who's controlling the pH? And well, sodium doesn't have any pH abilities. Water is a very weak acid or base. I mean, you think about Ka. Ka is 1 times 10 to the negative 14, right? Very small. The acetate right here, that is whining to go back to making acid. So this is also a conjugate base, so very strong. It's not going to control the pH. The thing that is controlling the pH is the acetic acid. So now I'm going to write a rice table, and I'm going to pause here, do a little bit of math, show you what we're doing just because we're getting short on time. Okay, so now since the acetic acid is the major contributor of the pH, you can see that I set up a rice table. And what's important to understand here is that the initial concentration, if you take a look at this 0.5 here, the 0.5 from this acetate comes from the sodium acetate. So that's what's new and unique when we're talking about a common ion in the rice table. And you probably remember that a little bit from when we were doing the sulfuric acid example. So as I build this rice table, and then again, AP would want you to write the expression, which is Ka then is equal to the concentration of the hydrogen ion concentration over the acetate, then over the acetic acid concentration. So now you'll notice that when we put in the information, which is 1.8, that's the Ka, is equal to then X, which is the hydrogen ion concentration, times 0.5 plus X over 0.5 minus X. And because of that 5% rule, we can indeed, with these concentrations, ignore, remember that amount of dissociation of X is not going to be very much. So we can say that X is also equal to the hydrogen ion concentration, which would equal 1.8 times 10 to the negative 5 molarity. That would be my concentration of hydrogen. And then the pH then would equal the negative log of 1.8 times 10 to the negative 5, where then the pH is equal to, I believe this is 4.74, is the pH. So it's a pretty simple concept with a buffer. The only thing that is unique is that there is this increase or this change in the initial concentration. It's not zero. You will have the conjugate species concentration in that table as well. Okay, that's going to set us up for another video here down the way. We're going to kind of simplify this expression too with a new equation called Henderson-Hasselbalch. So stay tuned for that. Good luck.